Modular speech encoder features, dubbed Lego features, are introduced as a novel approach to creating interchangeable features that can be seamlessly integrated with different versions of encoded representations without requiring further fine-tuning. These features are generated by passing continuous encoded features through a tight discretizing bottleneck, rendering them powerful and informative for downstream automatic speech recognition (ASR) decoders. The authors adapt the beam convolution scheme to train streaming modular encoded representations, defining Lego features as the sorted top K connectionist temporal classification (CTC) logit indices at every frame, operating over a discrete space and grounded in the transcript text. These sparse features require re-embedding by downstream models since they come in as sparse indices. A key finding is that training the modular encoder from scratch under the CTC loss is insufficient for optimal performance. Instead, pre-training base encoder layers with RNN transducer (RNN-T) loss and keeping them frozen, followed by training extra exporter layers with auxiliary CTC loss, maintains the quality, latency, and efficiency of the base model. The authors also adapt the design to a streaming setting, making the Lego features compatible with a streaming-friendly RNN-T decoder. This streaming architecture exhibits strong downstream ASR quality and passes the modularity test, further evidence of the modularity and interoperability of the Lego features. Finally, the paper explores Lego features as an alternative to NBEST hypotheses within two-pass systems, providing novel comparisons against NBEST in terms of speed, accuracy, and modularity. In automatic speech recognition systems, a novel approach is presented for creating a modular, streaming-friendly, and cost-effective alternative for continuous encoding vectors and NBEST hypotheses. This is achieved through the introduction of Lego features, sparse, frame-level indices extracted from the connectionist temporal classification logits of an exporter model. These features can be used as input to various downstream models, such as RNN-T and LAS decoders, without any loss in quality or modularity. The framework consists of 3 stages: pre-training a base model, exporting Lego features, and training downstream models. The base model employs a cascade architecture with convolution layers and conformer blocks, pre-trained using the RNN-T loss. The exporter layers consist of additional conformer blocks with 180 milliseconds lookahead context, trained with a CTC decoder and loss. Lego features are computed by extracting the top K indices of the CTC logits at every frame. Downstream models consume these features by embedding them, followed by an importer module comprising 180 milliseconds lookahead conformer blocks. 2 types of ASR decoders are experimented with: an RNN-T decoder suitable for real-time applications and a full context listen, attend, and spell decoder that achieves higher quality by attending to all input frames. In a baseline comparison with second-pass deliberation ASR, the proposed method demonstrates success in the modularity test, as Lego features can be used as a first-pass output within the deliberation framework, achieving good post-deliberation word error rate performance. This approach also introduces speed gains to deliberation, without using the iterative align-refine approach. Lego features are cheaper to produce than NBEST hypotheses, requiring no beam search or auto-regressive decoding, and are generated via a simple projection at every frame. The proposed deliberation baseline model utilizes a fast RNN-T decoder to generate NBEST hypotheses, which are then embedded and attended to by a full context LAS decoder, as depicted in Figure 3. This setup is designed to have a similar model size and encoder latency to the full pipeline, comprising the Lego features encoder and decoder. The baseline model starts with a frozen base encoder, followed by a first-pass RNN-T decoder, producing NBEST hypotheses for comparison with Lego features in terms of informativeness and modularity. In the experimental settings, the quality of the Lego features encoder is evaluated through a preliminary CTC logit evaluation, where the full set of CTC trained logits is decoded using beam search or greedy decoding. The downstream ASR decoders trained on the Lego features are then evaluated, and a modularity test is performed to assess the interchangeability of different versions of the encoded features. The base architecture follows established guidelines, with 512 DIM conformer layers, 8-headed self-attention, and a convolution kernel size of 15. The models work with 4096 word pieces and a 128D logmul feature front-end with a 16D1 hot domained vector appended to it. The RNN-T decoder comprises a prediction network and a joint network with a single 640 DIM FF layer, while the deliberation decoder uses a 2-layer LSTM with 1536 hidden units followed by 384 DIM projection. The datasets used for training and evaluation are multi-domain audio-text pairs, with labels obtained in a semi-supervised fashion using larger teacher models trained on in-domain data. Data handling follows Google AI principles, employing techniques such as multi-condition training, random data downsampling, and spec-august to increase data diversity. Noisy data is generated at varying signal-noise ratios and T60 times to make the model robust to different environmental conditions. The experimental results show that the CTC decoder can be evaluated directly, with Table 1 presenting the CTC voice search WER performance for different exporter setups. The results indicate that greedy decoding performs close to beam search, with a slight degradation in performance. The modularity test results are also presented, assessing the interchangeability of different versions of the encoded features. A novel method for exporting streaming-friendly modular encoded representations is introduced, leveraging top CTC trained logits as a representation for first-pass automatic speech recognition (ASR) prediction. This approach demonstrates strong word error rate (WER) performance and interchangeability through modularity tests when tested with RNN-T and LAS decoders. The encoding process involves generating Lego features, derived from CTC trained logits, which outperform traditional NBEST representations in various aspects. These Lego features exhibit superior modularity, quality, and generation speed compared to NBEST, making them an attractive alternative for ASR applications. The modular encoded representations are characterized by their ability to be easily combined and reassembled, allowing for efficient generation and modification of ASR predictions. This modularity is demonstrated through a series of tests, showcasing the flexibility and adaptability of the proposed approach. The findings of this research have significant implications for the development of efficient and accurate ASR systems, particularly in resource-limited environments. Future research directions include exploring smaller exporter and importer layers for on-device ASR and improving latency, as well as testing different types of Lego features with various downstream tasks such as confidence models, speech translation, and spoken language understanding. Please provide the content to be refined.